Now that everyone is well rested after the pause, we can resume. Okay. So my talk will be about the holomorphic locus in the moduli space of Riemann surfaces of genus G with n-marked points. When I rehearsed Witten's class, actually I arrived at the very end, but I decided it is good to take time. And it is a project that has been going on for several years. There are already 5 co-authors, and there will be maybe more people will join. So it is not even the final list of authors. Okay. So here is the picture which opens almost all of my talks. It is a pictorial introduction into the moduli space of curves. So here you see this big potato that is the moduli space of genus G curves with n-marked points. So it is the moduli space of stable curves. Stable curves can be smooth like these, or can have simple self-intersections like here. This is a simple self-intersection. And so in this case, I chose genus 2 and 3 marked points. As you see, every point in the moduli space corresponds to an algebraic curve of genus 2 with 3 marked points. If you take a generic point like this one or this one, the corresponding curve will be smooth. And then inside MGN bar, there is a normal crossing divisor. So there is one distinguished component, this one, that corresponds to curves with non-separating nodes. If you choose a point here, the corresponding curve has a non-separating node. If you normalize the node, the curve stays connected. Same thing here. This is a self-intersection of this component, so the curve has 2 non-separating nodes. And then there are several other components of which I represented only one, like this one, that corresponds to curves with separating nodes. So here the curve is separated into 2 genus 1 components, with one component containing points 1 and 2, and the other one containing point 3. And this is not at all the only possible choice, so there are many components like that. Okay, and thanks to this picture, we can define n line bundles over MGN bar, L1, Ln. So let me draw L1. So if we're interested in L1, we pick the first marked points and we draw the cotangent line to the fibers of this map. So the cotangent line to our algebraic curves at the first marked point. It is so over every point in the moduli space, there is a red complex line floating above it. And if you take the union of all these lines, they form a line bundle L1. So there is a line bundle over MGN bar for every marked point. So there are n of them. And we can define the psi classes, which are the first term classes of these line bundles in H2 of the moduli space. So maybe for completeness, I will also define the kappa classes. If you see this for the first time, you will still be able, so I realize it is a very fast introduction, you will still be able to follow most of what follows without knowing what are the psi classes and the kappa classes, except that sometimes there will be formulas that's, well, where they appear. So kappa m is the push forward of psi n plus 1 to the power m plus 1. If you take the forgetful map from mg n plus 1 bar to mgn bar, forgetting the last marked points. Okay, and there are also, so these are cohomology classes. maybe I'll write that this one is an H2M. So these are cohomology classes in the moduli space. And also every boundary component or every boundary stratum determines a Poincaré dual cohomology class. So when we're interested in the, well, when we work in the cohomology ring of MGN bar, we have many classes to work with from the start by using the boundary strata and the boundary components. So the components of this divisor and their intersections, and also psi classes and kappa classes. Okay, so now let me define the holomorphic locus, which is the main character of the talk. So first I define it in MGN. Holomorphic, okay, A1, AN. So I fix n integers, A1, AN, A1, AN, is greater than or equal to 0, and their sum is equal to 2g minus 2. That's the number of zeros of a holomorphic one form on a genus G Riemann surface. So then this holomorphic locus is the set of curves of genus G with n marked points inside MGN, such that, so there are different ways of saying it. Let me write the shortest way with letters. Omega of minus sum of AI xi is the trivial line bundle. So I will now say other ways of what it means. So omega is the canonical or the cotangent line bundle, to C. So its sections are holomorphic one forms or abelian differentials. A holomorphic one form on a genus G surface has 2g minus 2 zeros. And what I require here is that the zeros are precisely at the marked points x1, xn, and their orders are precisely a1, an. Or maybe let me write this with letters. There exists a holomorphic one form alpha on C, such that the zeros of alpha are at x1, xn, and their orders an. Okay, so this is what is called the holomorphic locus, or the locus of curves that carry a holomorphic differential. And it is the same as saying that the line bundle, that the cotangent line bundle twisted by the divisor minus sum of AI xi is the trivial line bundle. Okay, so this is the definition of the holomorphic locus. So this is important to remember because I will discuss this for the remaining 50 minutes. If there are questions on this, please ask. Okay. And so I will also denote in the same way its closure, holomorphic A1, AN. In MGN bar, it's just the closure. So it is an interesting question, what actually lies in this closure. We will meet an example soon. So far, I just define it as a closure. Okay. So there is a theorem by Polishuk. Maybe I can write it in Russian. Really a pain to write in English. So Sasha's Polishuk theorem that says that the holomorphic locus let's say in MGN. In MGN is smooth and of pure codimension G minus 1. So it is not necessarily irreducible. Maybe I'll write that too. Not always irreducible. Connected components were classified by Kontsevich and Zorich, so there are between 1 and 3 connected components. But it is always smooth, and all the connected components are always of the same dimension, G minus 1. And so G minus 1 is a little bit unexpected. What you might expect is a codimension G first, because well, you have this this line bundle. So it's a line bundle of degree 0. It corresponds to a point in the Jacobian of the curve. Here's the Jacobian of the curve. The Jacobian of the curve is a complex torus of complex dimension G. And we have this point that corresponds to the trivial trivial line bundle, and we require them to be the same. So in principle, when you have 2 points in a complex torus of dimension G and you require them to be the same, you expect that this is a condition of codimension G. But in this case, it is actually a condition of codimension G minus 1. And the reason is that omega has an H1. So if we make a computation, I don't know if I have enough room here. So omega has the dimension of the space of sections. The dimension of the space of abelian differentials is G. The projectivization of this space has dimension G minus 1. And this is the space of all abelian differentials up to a constant. And then you impose 2G minus 2 conditions for the zeros of the differential. So first, on every curve, you have something of, well, you have a space of dimension G minus 1 of possible holomorphic differentials up to a constant. Then you impose 2G minus 2 conditions. So in the end, you get codimension G minus 1. Okay. So let's do an example. Example genus 2. So it is well known that every genus 2 curve is hyperelliptic. And let us recall the way it is proved, because it is related to holomorphic differentials. So actually, so on the genus 2 surface, there is the space of holomorphic differentials has dimension 2. So we can choose a basis alpha beta. And every holomorphic differential has 2G minus 2 zeros, so 2 zeros in this case, which can be 2 distinct zeros or 1 double zero. And then we take a function alpha over beta. So this is a meromorphic function that has poles where beta has zeros and zeros where alpha has zeros. It goes to CP1. And okay, so alpha and beta have 2 zeros each. So in principle, we expect F to be, and it is easy to see that this is actually the only possibility. If, well, F cannot be of degree 1 because here you have genus 2 and here you have genus 0. There is no map of degree 1 between a genus 2 surface and a sphere. F cannot be of degree 0 because if F was of degree 0, that would mean that alpha and beta have the same zeros. so they're proportional to each other. And this contradicts my assumption that I chose a basis. So that means that if I choose two linearly independent abelian differentials, they do not have any common zeros. It is not possible, so they cannot have two common zeros because then they would be proportional to each other, and f would be just a constant. And they cannot have one common zero because otherwise f would be an isomorphism between two surfaces of different genera. This is not possible. So it is always, this map is always of degree 2. And the Riemann-Hurwitz formula tells you that it has exactly 6 branch points. You can even kind of see them on the picture. I'm a little bit cheating, but not so much. So these are the branch points. So if you take, they're called the, so these 6 points are the Weierstrass points. Weierstrass points on the surface, on the curve C. And if you take any point here, different from the 6 branch points, it has 2 preimages. And these 2 preimages are 0 of some holomorphic differential. And if you take one of these points, well, it has 1 preimage, and this preimage is a double 0 of a holomorphic differential. So the Weierstrass points are precisely the points where a holomorphic differential can have a double 0. So what do we see? We see that there are exactly 2 interesting cases. Hol 2, the locus of holomorphic differentials with a double 0, and the locus of holomorphic differentials with 2 simple zeros. I can also add zeros. So when I picked my integers ai, I told that they were non-negative. So zeros are allowed. I could add zeros, but these would be just pullbacks of these 2. So there are these 2 basic cases, and everything else is a pullback. So this is the set of the locus of genus 2 curves with a marked point, such as x is a Weierstrass point. And this is the locus of curves, genus 2 curves with 2 marked points, x1 and x2, such that x1 and x2 are conjugate by hyperelliptic involution. So if we look at the previous page, these are the 2 points that are conjugate by under the hyperelliptic involution. They have the same image under F. So these are our 2 holomorphic loci, and our goal will be find the cohomology class, Poincaré dual to the holomorphic locus. And maybe I will add in MGN bar. I am asking the harder question. I could ask the same question in MGN, and this is a sub-question of the harder question to find the locus, the class in MGN bar. Okay. So let me see if I counted my pages right. If I counted my pages right, you will see the answer to this question in these 2 cases on the next page. Now I see okay, here it is. So I left one extra page. So here's the answer in genus 2. It is not particularly useful, to be honest. I just felt stupid not to give it since there are explicit formulas. So you cannot, there is no need to stare at these coefficients and try to guess what they are. The only thing that you can notice is that I am using the cohomology class that I defined on my first page. So you see the psi classes, And here you see boundary divisors. So this picture represents, these two pictures represent two boundary divisors in M21 bar. This is the boundary divisor of curves with a non-separating node. This is the boundary divisor of curves with a separating node. In this case, there is only one. And in this case, there are, in the other case, there are several. And it is a linear combination of these pictures with some coefficients. And also you can notice that the codimension is equal to G minus 1, which is 1 in this case, since I'm in genus 2. So all these are boundary divisors. The curves have only one nodes. When you see psi classes, they appear in degree 1. But if I go to genus 3, I will have codimension 2, so pictures will be more complicated. Okay. So let's try to solve this problem. Now I formulated a problem, find the cohomology class Poincaré dual to the holomorphic locus. Let's try to solve it. To do this, I start with a very short exact sequence. 0 goes to the trivial line bundle, goes to the line bundle O twisted by sum of AI xi. Okay, so this is the sheaf of functions that are allowed to have poles of orders AI at the point xi. This is just the sheaf of holomorphic functions. Right. So I can use the Serre duality to write a dual exact sequence. Sorry, so here, it's not even, yeah, sorry. So just, yeah, right, so sorry.
Because when you say Poincaré dual, you mean that we have orbifold and we have like rational Poincaré duality?
So far, no, sorry. This is on C, this is on C. There are no orbifolds, this is on C. This is really the simplest thing possible.
But when you consider like MGN bar,
yes, yes.
So you say that like initial question is to find the Poincaré dual cohomology classes. So you mean that it's a orbifold Poincaré duality, or?
Yes. So MGN. Yes. So this is a good point. MGN and MGN bar are orbifolds. So their rational cohomology is just the cohomology of the underlying topological space. Mm-hmm. And the Poincaré duality holds over rational coefficients.
Okay. Mm-hmm.
So if you want to ask the same question over Z, this is much more complicated.
Mm-hmm. Okay.
I think the homology with integer coefficients is harder. Yeah. Yeah. Thank you. Thank you for the question. Yes, indeed. But right now I'm just on my algebraic curve. So I have these two line bundles. I have the spaces of sections. So these are constants. This is just this is just C, the space of constant functions, and then H0 of. So these are functions with poles allowed at the marked points. And now I take the Serre duality. So I take the dual vector spaces. Here I see omega twisted by minus AI xi. And now you can see why I did all that, right? Because this is precisely the line bundle I'm interested in. And this goes to C, the dual of this one. This goes to 0. So this is a surjection. This is called a cosection. It is a surjective map from this space to C. Right? So now let's look at this sequence away from the holomorphic locus. So away from the holomorphic locus, omega of minus AI xi is a non-trivial degree 0 line bundle. Non-trivial precisely because I'm away from the holomorphic locus. Therefore, its H0 of C and this twisted omega is equal to 0. A degree 0 line bundle can have a section only if it is a trivial line bundle, the trivial line bundle. Therefore, H1, this H1 here, maybe I'll just denote it by H1, the same H1. So has dimension G minus 1. So away from the holomorphic locus, these H1s always have the same dimension G minus 1. And this means that they actually form a vector bundle of rank G minus 1. It is an exercise in algebraic geometry. If you have a if you have a sheaf that's with fibers of constant dimension, it is actually the sheaf of sections of a vector bundle. So H1s form a vector bundle that is called R1 pi star tree of the twisted omega. And this has rank G minus 1. So if we compute the Chern classes of this vector bundle, first of all, we know that the Chern class number G, for instance, will be equal to 0 because it's a vector bundle of rank G minus 1. So the Chern classes beyond the rank vanish. But I claim that also CG minus 1 of R1 is equal to 0. And this is because of the cosection. Because we have a surjective map from R to the trivial line bundle, from R1 to the trivial line bundle, right? So if you have a vector bundle with a surjective map to the trivial line bundle, you can decompose the Chern class as the product of 1 that corresponds to this and the Chern class of the kernel. And the kernel is a vector bundle of rank G minus 2. Okay, so now look, we have this wonderful cohomology class of degree G minus 1. Notice that this is exactly the codimension of the holomorphic locus. This is the right codimension. And we know that it vanishes equals 0 away from the holomorphic locus. So this seems to be like a good candidate for the answer, right? We have a cohomology class of the right degree that vanishes away from the holomorphic locus. So that proves already that it is, well, that it is a linear combination, right, of components of the holomorphic locus. Maybe, so we don't know if the coefficient is 1, but if we're lucky, the coefficient should probably be 1. So this is a good candidate for the answer for the to compute the holomorphic locus. So the question is this the answer? Is this the answer? Well, not entirely. So let me tell you exactly the situation.
So, sorry, Dima.
Yeah.
But if it would be just proportional to the required class, it would be also a nice candidate.
Yes, but it is actually so with this. So here I miscalculated the number of pages in the opposite way. So I have to erase something. Let me go back maybe and erase all this. Maybe there is a clear page. Clear page. Oh, very good. So, okay. So here are the two claims. Claim 1. Claim 1. This class, CG minus 1 of R1, is computable by the Grothendieck-Riemann-Roch formula. And claim 2. This is the right answer. The right answer for the holomorphic locus in MGN, but not in MGN bar. So we have already obtained something. Actually, my explanations were perfectly honest on MGN. They need to be made a little bit more precise, of course. It is called the Thom-Porteous theory, but it is indeed the correct way to find the holomorphic locus in MGN when we only have smooth curves. So let me illustrate the claim 1. I say that this is computable. So let's go to the, this is the answer in MGN. This is in MGN. Okay, so let me read it all aloud because there are lots of letters. So first of all, I define the Bernoulli polynomials. Well, you can look at Wikipedia. These are very famous polynomials defined by the Taylor expansion of this function, t e to the xt divided by e to the t minus 1. And if you expand that in t, the coefficients are polynomials in x, and they are called the Bernoulli polynomials. And if you plug x equals 1, you can plug x equals 1 in the original formula, by the way. So you get the Bernoulli numbers. And the holomorphic locus in MGN is expressed from kappa classes and psi classes. So again, you can see here the kappa classes and the psi classes. And the coefficients are Bernoulli numbers for the kappa classes and values of the Bernoulli polynomials at ai plus 1 for the psi classes. So for those who know Mumford's formula for the lambda classes, it is very similar to this formula. And the reason is that because it's a very similar computation with the Grothendieck-Riemann-Roch formula. Okay, so this is a beautiful answer, slightly complicated. Yeah, two more remarks, sorry. So first of all, this thing that I wrote here is a mixed degree class. As you see, there are kappa classes of all degrees and psi classes of all degrees. You sum for I from 1 to m. You sum for all m's greater than or equal to 1. So you get a mixed degree class. And then you extract the degree g minus 1 part to get the holomorphic locus. And another remark is that, remember I told you that there may be a coefficient between cg minus 1 and never mind. So that there's this coefficient minus 1 to the power g minus 1. Yeah, it's not even there. I remove my second remark. Okay, so this is the answer in MGN. A little somewhat complicated, but still a very beautiful formula with Bernoulli numbers and Bernoulli polynomials. But unfortunately, it does not work in MGN bar. So let me explain why it does not work in MGN bar. What goes wrong in MGN bar? So let's look at genus 2 again. My example is again at genus 2. Let's look at this locus. And specifically, so now that I am on the space of stable curves, I don't look at smooth curves, I look at stable curves. And specifically at stable curves like this. So this is the point X, and this is a simple self-intersection. This is a stable curve. So what I say is that this boundary locus, so this is a boundary divisor, one of the boundary divisors. So I say that this boundary divisor is not in the closure of the holomorphic locus, but participates, appears in C1 of R1. Computation. So let's try to understand both points. Why it appears. So let's first understand why it appears in the computation of C1 of R1. So remember how I reasoned when I proved that this thing vanishes away from the holomorphic locus. I said away from the holomorphic locus, this twisted omega is not the trivial line bundle, so it has no sections. Is not O, and therefore it has no sections. And this conclusion is actually wrong if you look at stable curves. So on this stable curve, we take omega of minus 2x. So we're trying to find holomorphic one forms with a double zero at x. And so indeed, this is not the trivial line bundle. This is correct. This is not the trivial line bundle, but nonetheless, it has sections. It has the following section. It is identically equal to 0 on the left component. And it is a holomorphic one form. So one form on the other elliptic curve. So there are two elliptic curves. As you know, on every elliptic curve, there is one unique holomorphic one form up to a multiplicative constant. So on this curve, on this elliptic curve here, I choose any holomorphic one form. They're all proportional to each other. And on the other one, on the left one, I choose the holomorphic one form that vanishes identically. And since it vanishes identically, it does have a double zero at x, or even a triple zero, zero, zero of any order. So I have a problem. This is true. I am away from the holomorphic locus, so this thing is not the trivial line bundle. But the thing is that it is actually a line bundle of degree -1 on one component and 1 on the other component. And so the line bundle of degree -1 doesn't have any sections, but the line bundle of degree, yeah, no, it's not even, yeah. Sorry, I erase this because it's a little bit more subtle and I don't want to, to confuse you. So it's not the trivial line bundle, but nonetheless, it has a non-trivial section that vanishes identically on one of the components. And therefore, so R1 not a vector bundle on this locus, and so I cannot conclude that C1 of R1 vanishes on this locus. It's just not true. And indeed, if you make the computation carefully, you will see that C1 of R1 in this case is equal to the holomorphic locus plus this boundary divisor. So in genus 2, it is not such a huge problem because now that we understand this formula, it is easy to subtract the parasitic term and get the answer for the holomorphic locus. It is one of the ways in which you can compute it. But if you go to higher genus, you will meet this problem more and more often. And I mean, it will become more and more complicated. So so it just doesn't work. Okay, now I have a strategic decision. So there is one other thing to explain why this boundary divisor is not in the closure of the holomorphic locus. So let me say a couple of words briefly, because otherwise it will be a little bit long. So I claim that this thing here, x, let me denote this point by y. And this component will be E1 and this component will be E2. So I claim that this curve lies in the closure of the holomorphic locus. So x is the limit of the Weierstrass points on genus 2 curves, if and only if x minus y is 2 torsion on E1. And the way you prove this is a little bit funny, but it's very unusual in algebraic geometry. And instead of using usual tools from algebraic geometry, you use something that is more like glue and scissors. So when you have an elliptic curve with 2 points, so when you have two points on an elliptic curve such that their difference is 2 torsion, you can find a doubly periodic function that has a double zero here, right? So let's say omega of 2y minus 2x has a section alpha on E1. So on E1, you can find a meromorphic one form with a double zero at x and a double pole at y. And it will look like something like this. So suppose you have this is the plane. You take dz. This is a one form. You take a parallelogram inside this plane. You cut it out, and now you glue this interval to this interval, and this interval to this interval. So what you will obtain is an elliptic curve. This point, so this point will be, these 4 points will be glued together, and this will be the point x, and restricted to this elliptic, well, on this elliptic curve, it will have a double zero at x, and then there will be the point y that is the infinity. So at infinity, dz has a double pole. So this is one picture. And on E2, I erase because I have to make another picture. On E2, we just have beta, which is dz on the parallelogram, and again, you glue the sides of the parallelogram. Oops. And you get an elliptic curve. And this is a holomorphic one form on this elliptic curve. This is well known. And so now I say that you can glue this inside this. You can deform. So now you have a meromorphic one form here, alpha, let's say, and a holomorphic one form here. And I say that you can deform it all to get a holomorphic one form on a genus 2 surface. And what is the way to do it? You make a very small hole and look at it with a magnifying glass. And you glue all of this picture inside the small hole. Right? And then you get, okay, so you get a genus 2 surface, and it has a double zero with a holomorphic differential, and it has a double zero at this point x. And the point y disappeared. The point y, so y was the node, and it got resolved when I glue this disk, this big disk into this small disk. The point y disappears. So you'll have to think about it. It's a very nice construction. Okay, but so anyway, the outcome of this is that our first attempt at solving the problem failed. And now I have 15 minutes to tell you about the second attempt. So here's the second attempt. We take a line bundle L over C, whose rth tensor power is isomorphic to this twisted omega. So there are actually many line bundles L like that. They are called R-spin structures, and there are R to the power 2g of them possible L's. If I draw the Jacobian of C, and here I have the point that corresponds to my twisted omega, and now I want to divide it by R. So let's say on my picture, I will take R equals 3, for instance. So then I will divide this by 3. And this is one possible L. This point corresponds to a line bundle, and this is one possible L. But once I find one possible L, I can add any 3 torsions, so R torsion points to it. And all these things, when multiplied by 3, will also give omega. So in general, there are R to the power 2G points, like in complex dimension G, so real dimension 2G. Okay. And now I would like to repeat repeat all of my, so let's look at my notes. Repeat the same reasoning. Repeat the same reasoning with this L. So away from the holomorphic locus, L is never trivial. So L is a degree 0 line bundle here. If it is trivial, then when I raise it to the power R, this one is also trivial. And that means I'm in the holomorphic locus. So away from the holomorphic locus, L is never trivial. And again, I can use the same reasoning to say that R1 I star L is a rank G-1 vector bundle. Now on the holomorphic locus, okay, so let me show you what happens. So let me show you why this thing helps in genus 2. So this is M21 bar. This is the holomorphic locus hol 2, so with Weierstrass points. And this thing is my parasitic component. So this is the locus of curves like that. Okay. So over a generic point, here I have R to the power 2G points corresponding to different L's, but none of them corresponds to the trivial line bundle. So no trivial line bundles. If I take a point in the holomorphic loop, let's draw it in green because this is the favorable situation I'm looking for. So this point will also have R to the power 2G preimages, of which one will be trivial. And then all the others will be R torsion line bundles, non-trivial. So this is O, and these are R torsion. Right, so as I said, so this is O, since I'm in the holomorphic locus, so my twisted omega on the holomorphic locus, my twisted omega is trivial. So here my twisted omega is the trivial line bundle, and one of the rth roots of the trivial line bundle is trivial. The others are not. So this thing has a section, but on these R to the power 2G minus 1 sheets, R1 is still R1 is still rank G-1 vector bundle. And now the interesting thing happens on this locus, the red locus. So this is the bad locus that I want to eliminate. And something interesting happens here. So here, remember the reason it appeared in my computation of C1 of R1, omega has a non-trivial section here that is isomorphically equal to, identically equal to 0 here and holomorphic non-zero here. So now, if I want to find an rth root of this line bundle, I want to find an rth root of this line bundle that has a section. Well, so okay, I restart my sentence. So here I still have r to the power 2g preimages. This doesn't change. The question is, how many of these preimages have sections, have non-trivial sections? The answer is, well, if I have a non-trivial section here, I can raise it to the rth power and obtain a non-trivial section here, which I know. And so this non-trivial section vanishes identically on the left-hand side component, which means that on the left-hand side component, I can choose any rth roots of my line bundle. Maybe I should write somewhere here, r to the power L to the power R equals twisted omega. So on this curve, I actually have I have two components. So I have two cotangent line bundles of the two components. And for the first one, I can choose any line by any rth root I want. Anyway, the zero section always exists. And for the second one, I will rth roots. So here I will have r to the power, so r squared, let's say here, if I write the total number, since I'm in genus 2, it will be r to the power 4. So here it will be r to the power 4, r to the power 4. Every point has r to the power 4 preimages. But now I see three different situations. For a generic point, none of these has a section. For a point in the holomorphic locus, exactly one of these has a section. For a point in this parasitic locus, r squared have a section. So that means that if I now compute CG-1 of L and project it to MGN bar, I will be able to distinguish between these two components because they will come with different powers of R. So now I have 5 more minutes, right? I will just confess 2 places where I lied. One of these places makes appear Witten's class. Well, I didn't really lie. Oh, sorry. This was supposed to come a little bit later, in 5 minutes, but you already get the idea. So I go 1 page up and I raise this page. Yeah. So 2 places where I lied. Okay, I didn't actually lie, but I led you to believe that CG-1 of L vanishes. I get some strange echo. Someone must have switched on the microphone. So CG-1 of L. So actually now there is no reason for it to vanish. What vanishes here is CG-1 of L minus Witten's class. So R spin Witten's class A1 AN. So remember before when I told you about CG-1 of the twisted omega, R1. So this R1 here, R1 of the twisted omega, is a rank G minus 1 vector bundle. In principle, when I have a rank G minus 1 vector bundle, its G minus 1th Chern class does not vanish. But this one does vanish because there was this cosection that goes to C. So now this R1 again is a rank G minus 1 vector bundle, but things are not this simple any longer. So there is no such a cosection, but there's a general section that is not linear, and there's a whole theory about how to construct virtual fundamental classes with cosections. Sorry, and this is one of the. Oops. What happened? I went somewhere very still. Okay, and this is one of the ways to define Witten's class. So there is an analog of this cosection, but it is much more complicated in the case of Rth roots, and it requires a complicated technical paper to define to kind of reduce the degree of the class. Instead of just saying, well, CG minus 1 of this vanishes because of this cosection, here you need to do this whole construction, define Witten's class and subtract one from the other. So what is true is that when R minus 1 is a vector bundle, R1 is a vector bundle, Witten's class is equal to CG minus 1. So away from the holomorphic locus, when this thing is a vector bundle, these two things agree with each other, and when you subtract one from the other, you get 0, which is what we want. We want something concentrated on the holomorphic locus. And on the parasitic components, you do get extra contributions, but they all come with higher powers of R. And so this will be my last formula. C1 of R1 pi star of L minus Witten's class in genus 2 over R is equal to the holomorphic locus plus R times the parasitic locus here. And this is the other place where I lied, because if you look at my picture on the previous page, you may think that the coefficient would be R squared. And actually it is R, because these points here also have a stabilizer, orbifold stabilizer of order R, so you divide the answer by R. I don't want to go into this, but I want you to understand that the origin of this R is the number of sheets above. Okay, and so this is again computable. And well, this thing here, as you see now, it is a polynomial in R. And if we take the constant term, it gives you the holomorphic locus. So this was the conjecture that was in my abstract, that if you take the difference between, so if you take this thing here, it is a polynomial in R. This is proved. And the conjecture is that the constant term is the holomorphic locus. So today I kind of motivated this conjecture. It is actually almost proved, but not in here. It's exactly 1 hour. Thank you very much. Up. That was.
Dima, thanks a lot for the cake, especially. May I ask a question?
Yes.
What kind of an answer you would consider to be computable? And is there any reasonable way to find out the constant term of this polynomial in R, provided the conjecture will be proved?
Yes, so this is actually a very good question. Okay, so the thing is, for every R, there is an explicit formula Witten's class and for this CG minus 1 in terms of a Riemann-Roch computation. An explicit formula means sum over stable graphs labeled with psi classes and kappa classes. And for every stable graph, you get a coefficient. It is a complicated formula because the conjuring of the moduli space is complicated, but it is as explicit as it can be. Just for any generator, the coefficients. All because now you would like to so this is a polynomial in R, and you would like to find its constant term. And the thing is that the polynomial in R not in a very straightforward way. It is actually very similar to the Erhard's polynomials, which count the number of points, integer points, polytopes of growing size. And so the coefficients of these polynomials are not so simple to compute. Compute things by hand in small examples, it's actually always easy to figure it out, but it's not really a closed formula. So in practice, I mean, there is a computer program that does that, and in practice, what it does is compute for several R's, and then guess the polynomials by, guess the coefficients of the polynomial by just fitting the values. You can say, we know the degree of the polynomial, so we can how many values to compute in a very satisfactory way.
I have also a question.
Yes.
Is there an independent way to compute intersection numbers of the holomorphic locus with some tautological classes? For instance, as far as I remember, there were some formulas for integrals of psi classes over the modular spaces of holomorphic differential of abelian differentials. So I mean that check if the formula is true, then one can check by intersecting both sides with some.
Yeah. So I don't think there are any closed formulas. There is an algorithm. There is an algorithm if you want to compute. So in general, there is an algorithm to compute the holomorphic locus by induction, which starts. So this is the work by Adrien Sauvage, where you start with the projectivization of the Hodge bundle, and then impose one by one the conditions that the differential vanishes at the marked points, and at every step you get the locus of differentials with zeros at the marked points, more and more zeros at the marked points, and some parasitic components that you can remove. So the main point of his work was to enumerate all the parasitic components that you have to remove. So in principle, there is an algorithm to compute the holomorphic locus, but it is extremely slow and inefficient. It can be actually sped up if you're interested in a particular intersection number. So I know that for some intersection numbers, there were, I'm just afraid to say something stupid. Yeah, so, yeah. So actually, in some cases, they're related to the Ziegel-Veitch constants. This is the, so if you take the holomorphic locus and you compute some intersections with psi classes, but very particular, well, particular intersection numbers, you get Ziegel-Veitch constants for the holomorphic locus. It's right. This is precisely the thing for which the Ziegel-Veitch constants are defined.
Okay, just because as long as I see some theorem claiming some equality, for me it makes sense only if I can compute independently both sides. If I can compute only one side, I can call this not a theorem but a definition.
Yeah. So yeah, both sides are sides, but it is difficult in both. I mean, both sides are difficult. So there are two independent definitions. If you are very patient, you can program. I mean, some of them are actually programmed. There is a.
Okay.
There is a. Do you know Johannes Schmidt's package?
I hear it. Yeah.
Yeah. Okay. So. So there are two independent ways to compute numbers and check. I'm not sure anyone did that beyond genus 2. I mean, in genus 2, we checked everything.
Mm-hmm. Thank you.
А кто тортик рисовал?
Ну, я нарисовал. Такой тортик я могу нарисовать. Похоже на Петю больше, наверное.
Да, вот я и спрашиваю.
Мы с ним уже сравнивали в рисовательских талантах.